Hi guys, and welcome to the Start of Mechanics. This is the second of the applied modules that you'll learn this year. You do incidentally do statistics and mechanics again next year, but this year we're just going to cover the basics and mechanics. We'll be looking at connected particles. So the situations where you have, for example, a truck pulling a car, or you have maybe a car pulling a trailer or something like that. So you have this fixed rigid connection between the two objects, and we'll be looking at working out the acceleration of the system, the tension in the connection. If it's a tow bar or something, what's the tension in that tow bar, and taking into account any frictional forces as well. So that's one type of problem. The other connected type of problem is where you have a pulley system. So you might have just two objects connected over a single pulley, and we'll be working out the tension in the string and the acceleration of the system. The third type of problem that's quite common is where you have an inclined slope and you have an object that's on the slope, and again maybe there's friction involved there, and the object is connected via a pulley and a wire or a string to another object that's vertical, that's hanging vertically. And again, you want to work out the tension in the string, the acceleration. Perhaps after a certain amount of time the string breaks, and you want to work out the maximum height of the object up the slope and how long it takes to get to that maximum height. So those are the type of problems that we'll be looking at in mechanics. So we're going to start off by looking at mathematical models. So just a brief outline of what is a mathematical model and how can we apply it in mechanics. We'll be looking at modelling assumptions and how we can refine our modelling assumptions to improve our models, and looking at SI units, so the standard units that you need to work in when you're answering questions in mechanics, and also a little bit on vectors as well. Okay. So, constructing a mathematical model. Mathematical models are basically a mathematician's way of predicting things that happen in real life or solving a particular problem. So, as an example, let's say you go out into a field, you got a cricket ball, and you throw the cricket ball. You want to work out the motion of that cricket ball as it flies through the air. Perhaps you want to come up with a formula that predicts the height of the cricket ball after a certain amount of time. Well, you have to have some assumptions to try and simplify your mathematical model in the first instance. So you might want to assume that, for example, there's no friction, maybe there's no air resistance. Maybe you're going to model the cricket ball as a particle, so it will have a mass, but it won't have any dimensions. Perhaps you just want to model the only forces acting on the object are due to gravity. Okay, so there's no horizontal forces acting on it. It's just gravity pulling it down. Things like that. Yeah, so modeling assumptions that you would need to write down, and the variables that you're going to use in your formula to predict the height after a certain amount of time. So what variables are you going to use? You might want to use h for height, t for time, and so on. So you'd need to write them down. Okay, so then you come up with a mathematical formula which gives you the height based on the amount of time. And you go out and maybe you can actually measure in practice. You measure the height of the cricket ball after a certain amount of time, and you're going to compare your theoretical formula, the results from your formula, with real life. Okay, so you're comparing theory with practice, and perhaps your model gives a good answer, but more likely it's gonna be a little bit off. Okay, maybe it needs refining. So we have this whole iterative approach whereby we go back and we reconsider our assumptions, we modify our assumptions, maybe we take friction into account, and so on. We then compare our new formula with practice, and then maybe do this 2 or 3 or 4 times just to refine our model until we get answers from our theoretical formula, from our theoretical model, which more closely compare to reality. Okay, so that's the whole process of working out a mathematical model, refining it until we get a model that's adequate for our needs. Okay, and then we would just report our solution as a formula. Okay, so you just really need to be aware of that process. And in this course, all you'll need to be able to do is to, first of all, understand what the assumptions are doing to your equations. Okay, so for example, you might want to ignore resistance, so there'll be no term with resistance or friction in the model. But more importantly is to understand how the results from your mathematical model compare to reality. Do they make sense? Yeah, and we'll be looking at a couple of examples where you get results which actually don't make sense in reality. So you just need to be aware of that. Okay, so let's just take a look at an example. Here we have the motion of a basketball. Okay, so you've got a basketball player, he's trying to throw the basketball into a net, and we've come up with an equation, which is a mathematical model, which predicts the height of the basketball as it leaves the basketball player's hand. Okay, so we've denoted h to be the height of the basketball. That's one of our variables. X is the distance, horizontal distance from the basketball player, and this model predicts the height above ground. Okay, so first thing we need to do is to find the height of the basketball when it's released. That's the first part there, and when it's at a horizontal distance of 0.5 meters. So we're going to go over this together. We're going to do this one together. So part A, section I, we're going to use this equation to work out the height, but it says when it's released. Okay, so when it's released from the player's hand, we're actually at a distance of 0 from the player's hand. Okay, so x is going to be 0. So all we have is h equals 2 plus 1.1 times 0 minus 0.1 times 0 squared, which is just 2. Okay, so that kind of makes sense. I guess the ball is at 2 meters as it's released from the player's hand. Okay, and part 2, it says the height of the basketball when it's 0.5 meters from the player. So that's when x equals 0.5. So again, it's just a case of putting this into the equation, into the model, and working out what the height is. So just replacing x with 0.5, and you can put this into your calculator and work it out. You actually get a value of 2.525. Okay, it might be a good idea just at this point in time to talk about accuracy of your answers. In pure maths, all your answers need to be spot on, exactly accurate, exact answers sometimes, so answers in terms of surds or fractions, not decimals. In mechanics, it's slightly different because sometimes we use, for example, gravity, and we're approximating gravity in maths as 9.8, which means that all of your answers should really be, the final answer should be approximated to 2 significant figures. Because this is a mathematical model, again, writing down a too accurate answer may not really make sense. So I would probably write this down as 2.5. This isn't going to be exactly the right height. This is just an approximation for the height, because we haven't taken into account, air resistance and things like that. So it's probably sufficient to give this answer to 2 significant figures. And when you do that, just indicate in brackets how you're rounding your final answer. Okay, so 2.5 meters above the ground after it's traveled 0.5 meters horizontally. Let's move on to part B. It says, use the model to predict the height of the basketball when it's at a horizontal distance of 15 meters. Right, so we just need to do the same thing, but we're going to put 15 in as our value for x. Okay, so again, just pop that into your calculator and work out the value. We actually get a value of -4. Okay, does that make sense? This is where the question is going to test your kind of understanding of real life. interpreting this result of a minus 4 meters distance horizontally, that doesn't make sense, does it? If the basketball player is on a flat, court or whatever, then the ball's not gonna be below ground level, is it? So this wouldn't make sense. And part C is all about that. Comment on the validity of this prediction. This is a prediction that it's going to be 4 meters below ground level. I would say for part C, not valid for x equals 15 meters, as h is less than 0. Okay, so we wouldn't want to use this model for 15 meters, or perhaps slightly less than that. And that leads us to part D. Part D is asking us to work out the range of values of x for which the model is valid. Well, I would say that we want the height to be greater than 0. Yeah, for our model to be useful, it wants to give us results for positive heights. Yeah, at least greater than or equal to 0. So what I would suggest is that we try to solve this as an inequality. So 2 plus 1.1 x minus 0.1 x squared has got to be greater than or equal to 0. That's going to give us the range of values of x for which the model is valid. Okay, we're trying to work out the horizontal distances from the player that would give us a positive height. Yeah, we don't care about distances where the height is negative, like 15 meters. That's not going to be a valid value of x in our model. So in order to solve this, I think what I would start off by doing is just to multiply everything by 10, just so that we have integer coefficients. And then maybe just multiply everything by -1, just to get a positive x squared. That's always useful. And of course, when you do that, you need to change the sign of the inequality. So it becomes the opposite inequality. So if you multiply or divide by a negative, you need to swap that round. This one, unfortunately, doesn't factorize, so we have to use the quadratic formula. And when you do that, you get two values of x. So you get 12.6 and you get -1.6. Okay? Now, if I was to plot this quadratic, we'd get something that looks like this. Let's just see if I can use this to do it. Okay. And we just put in a couple of lines as well. And I don't know, maybe something like this. Okay, so let's just move that to the left a little bit. There we go, perfect. What I've done here, I've just drawn that quadratic inequality. Now, we want all values of x where the y value, which is this bit here, is less than or equal to 0. So all the values of x on this part of the curve, that's where the height is less than or equal to 0. Okay, so let's just mark that off. So it isn't the height that's less than 0, sorry, it's just this value. The height is actually positive on this part of the curve. It's because I multiplied by -1 that that it swapped it round. So here between these two values of x, the height is positive. Okay, so that's -1.6, and that is 12.6. Now, you might think, well, -1.6 meters, does that make sense? Well, that's actually behind the player, okay? And the reason that we've got that answer is because that would actually, if we went backwards, we'd actually get a height of 0 at -1.6 meters. Imagine this ball is flying through the air, okay? So here's the player, okay? And that's where he throws the ball. It comes up, hits the ground level over here. That's at 12.6 meters. -1.6 is behind him. Okay, and there's the floor. So you have to excuse my drawing, very, very quick. So we can disregard that because we're not looking at kind of backwards in time, if you like. So we only really want values of x greater than or equal to 0. Okay, that's how we're using this model. So the range of values of x is really between 0 and 12.6. Okay, so that would be my answer there. Okay, hopefully that makes sense. Let's take a look at another one. Incidentally, folks, if any of these examples don't make sense to you, then just bring them up in class and I can try and explain again. Okay, in this example, we have a car that accelerates from rest to 60 miles per hour in 10 seconds, and we're using this quadratic equation to model the distance travelled. So d we're defining as our distance in meters, t is time in seconds, and k is some constant that we need to work out. So for part A, it says given that when t equals 1, the distance travelled by the car is 13.2 meters, use the model to find the distance travelled when the car reaches 60 miles per hour, or meters per hour. I think it's miles per hour actually, but it's not clear, is it? So let's just write down what we know. So distance is 13.2, that's equal to k times t, which is 1 squared. So that's going to lead to k equals 13.2. Okay. Now we can use that value of k, that's going to be constant throughout the question. We're going to be using that value of k in the equation to work out d for any value of t. Now it does say at the start of the question that the car accelerates from rest to 60 miles per hour in 10 seconds. We want to know the distance travelled when the car reaches 60 miles per hour. Well, we know that's after 10 seconds, so that tells us what t is. So if you just put it back into the formula with k is 13.2 and t equals 10, we're going to get d is equal to 1320. So 1.3 kilometers. Okay, so far so good. Part B, this is where they're really testing your kind of understanding of the question in practice, in real life. Write down the range of values of t for which the model is valid. Well, we'd have to say that t's got to be greater than 0, or greater than equal to 0 at least. So for positive values in time. But what about the maximum value of t? What we really have here is another quadratic formula, another quadratic equation. So as t increases, d, the distance travelled, is going to increase exponentially. And obviously it wouldn't make sense for the car to be able to travel at 1,000 miles per hour or an infinite amount of an infinite speed. So there's got to be some restriction. And in the question it really only tells us the speed up to 10 seconds. Okay, so it reaches a speed of 60 miles per hour in 10 seconds. So I would argue that we can only really use this model up to 10 seconds. Okay, so you can write it like that, or you can just say the range of values of t are between 0 and 10. Okay, so another example there where you're kind of interpreting the results, and I quite often like to just throw in one little question at the end just to get you to think about the problem in practice and whether your results actually make sense. Okay, a bit of practice for you folks. Exercise 8A, have a go for homework, and any problems we can discuss them in class. Okay, so I've mentioned modelling assumptions, just a kind of note of warning really that some modelling assumptions you can't neglect. So for example, if you had a model which predicted the landing of a commercial flight, you wouldn't be able to ignore the effects of wind and air resistance because they'd be like very important in the actual model. And airline pilots do make significant adjustments for wind speed as they come into land. So certain things you can't ignore. Here's a list of modeling assumptions and how we modify our model. What do we do with the actual physical objects involved? How do we change them, and what modeling assumptions do we make? So as an example, a particle, we might model an object as a particle, which means that it has mass but it has no dimensions. It has no size. Okay, it's essentially any forces acting on the object act at a single point. Okay, and when we model objects as particles, it means that we're not going to take air resistance into account, and we can ignore any rotational forces on that object. Okay. Rods are like beams or poles, and again, we're going to assume they're only one-dimensional. Okay, so there's no thickness or no width to it. There's a length, but there's no other dimensions there. So it's a one-dimensional object. The mass is concentrated along the whole line. So if it's a uniform rod, then the mass is equally distributed along the length of the rod, and it's rigid, so it doesn't bend. Okay, so that's what a rod is if you're modeling an object as a rod. You need to be aware of all of these, particularly things like particles, rods, inextensible strings, smooth and rough surfaces, and pulleys as well are always frictionless. There's no friction involved when you have two objects connected via pulley. Air resistance, we normally ignore air resistance in this year anyway, and gravity as well. Okay, assume that that's constant, and we normally assume that gravity is 9.8. We approximate it as 9.8. Okay, so just have a read through them, folks. Just be aware of them. Here's a very simple example to do with modeling assumptions. So here we have an object that's connected to the ceiling via a light inextensible string, and you need to state the effect of the assumptions on the following assumptions on any calculations made with this model. So how would our calculations be affected if we assume the string is light and inextensible? And how would the calculations be affected if the mass is modeled as a particle? Okay, so what kind of things are we ignoring or taking into account? Well, for part A, if the string is light and inextensible, we're ignoring the mass of the string. In comparison to the actual mass that's connected to the string, it's probably negligible. So it might be really quite light compared to the mass. So we assume that it has no mass. And if it's inextensible, that means that when this object swings, it's actually swinging in a perfect arc, so a perfect part of a circle, the circumference of a circle. Okay, so in reality, maybe the string, if it's kind of like an elastic band, would stretch and we wouldn't get that uniform motion. For part B, modeling the mass as a particle, essentially what that means is that any forces acting on the particle just act at one point. So the tension is acting directly upwards from a single point, and the weight of the object is acting downwards, again from a single point. And essentially there'll be no rotation of this object. Okay, if you have forces acting at a point, they can't rotate the object. Yeah. So a couple of things to consider there. Okay, a little bit of homework for you folks. 3 questions. Question 1's about a goalkeeper that kicks a football from one end of the pitch to the other. What's the effect of the following assumptions on the calculations you make? So what's the effect of modelling the football as a particle or ignoring air resistance? In question 2, we've got a fishing rod manufacturer, and he's created a mathematical model for the behaviour of his fishing rod, but he's modelling it as a light rod. So again, describe the effects of that modelling assumption, and would it be valid to model a fishing rod as a light rod? Question 3 comprises 4 parts, so just have a little read through it, and here we just need to make a list of any assumptions that you might make.